namely, what is a positive quadratic form on a Hilbert space H is a function Q defined on a set dq with values in 0, infinity, such that dq in H is a dense vector subspace then Q of lambda xi is modulus of lambda square Q of xi for every xi in the domain of Q and lambda complex number. And third, it's Q of xi plus eta plus Q of xi minus eta. It's equal the 2Q of xi plus 2Q of eta, so that this kind of parallelogram law. And now, this positive quadratic form Q is said closed if it means that dq is complete with respect to the scalar product xi eta q is equal q xi eta plus q of xi and eta. And it's as an example of a closed positive form. So, example, you have a positive self-adjoint operator in H. And then you define the form associated to it, QA, with the domain of QA. It's equal to the domain of the square root of A. And for a vector in here, you have QA of xi. It's equal A 1/2 xi square. Okay. The first result is this proposition.
Excuse me.
Yeah.
I suppose you define Q xi eta by polarization.
You can get a bilinear form indeed by polarization, but I don't use it here.
No, but you said domain Q complete with respect to
The domain of Q sub A is
the second line.
here.
Second line Q
Yeah.
close, yeah. Look at the right extreme.
Yeah, of course, that's polarization indeed. Is the polarization of Q indeed. Yeah. Okay, and now the proposition is the following. If you have Q, a closed quadratic form, positive quadratic form, then you have a unique operator, A, positive self-adjoint, such that Q is the form associated to A. And this will be the method to define the spatial derivative as a positive self-adjoint operator. Okay. Now, a form is called Q is called closable. It means the following thing. It means it has a closed extension, but there is something more precise than this. Namely, if you have a psi n in the domain of Q, and if the norm of psi n tends to 0, and Q of psi n minus psi m tends to 0, this kind of Cauchy thing, then also Q of psi n tends to 0. And in this case, there is a minimal closed extension of it, which is denoted by Q bar. Okay. Now, in general, another proposition I will use here, proposition. If you have Q a positive quadratic form, then Q is closed if and only if Q is lower semi-continuous on H. Well, the quadratic form is not defined on the whole H, but on a domain, on its domain. But what is the meaning of this is that outside of the domain you put plus infinity, and then this makes sense. And the Q is closable if and only if Q is lower semi-continuous on the domain of Q only. Okay. So that we can state a theorem that we will use. You have Q on the domain of Q with in 0 infinity, a lower semi-continuous positive quadratic form. Then there is a unique positive self-adjoint operator A in H such that Q sub A is the closure of Q. That is, it est, that is, you have A 1/2 of psi square, it's equal Q bar of psi for every psi in the domain of A 1/2. That means in the domain of Q bar. And moreover, A to power 1/2 is the closure of its restriction to the domain of Q. So the difference is here you have Q bar and here you have just Q. And this is the theorem that we will use. Moreover,
You want to demand that.
sorry?
You should demand that the domain of Q is dense.
there is a positive such that you have a lower semi-continuous positive quadratic form. If you have a positive quadratic form, it means that the domain is closed, is dense.
Oh, because there you're talking about if it is not dense, you define it as.
But here, the domain of Q is dense by the definition of the positive quadratic form. Okay. So that, and moreover, A is the greatest positive self-adjoint operator such that the domain of A 1/2 contains the domain of Q. Notice it's about Q here, not about the closure Q bar. The domain contains the domain of Q, and A to power 1/2 of psi is equal Q of psi for psi in the domain of Q. So this is a better characterization of the operator associated to a lower semi-continuous positive quadratic form, because it avoids the closure of it. The positive quadratic form should be closable, that means lower semi-continuous on DQ, but in this formulation it doesn't appear, the closure. Just the fact that is closable, that means it is semi-continuous. Okay, so this is some preliminaries on the method to construct a positive self-adjoint operator. And now I pass to a second thing. It's again some preparation, namely we consider N in B of H a von Neumann algebra, and psi an NSF weight on N. Now, a vector psi, a vector eta in H is called psi bounded. That means the following thing. It means that there is a lambda positive such that you have B eta, it's less than lambda norm of B sub psi in the standard representation, is the GNS representation of the, and this is valid for every B in N, but in the N of sub psi in N. Okay, now we will denote by D H psi the set of all eta in H which are psi bounded, And then first result is that this domain is dense, a dense vector subspace in H. Okay, now each eta in this, each eta which is psi bounded in dH of psi defines a bounded operator denoted, it depends on eta and it depends also on psi. which is from H psi, which contains B sub psi, and it's going to be eta in H. This is for every B in N sub psi. This operator, so it's, let me write clearly here, R eta psi of B sub psi, it's equal to B eta. And this is for B in N, in the N of sub psi, which is in N. Okay. The properties of these operators are as follows. If you have an eta psi bounded, and if you have an element, an operator y prime in n prime, in the commutant of n, then you get that y prime of eta is still in dh psi, and r psi of y prime eta, it's equal to y prime r psi eta. This is one thing. A second thing is, if you take again a vector in dh psi, and you take an y in n, then you have y r eta psi, it's equal to r eta psi times p psi of y. What is the meaning of this equality? It means that this operator r eta psi intertwines the identity representation of n in B of h with the GNS representation of the y. Okay. Now, it will appear, but not very much, the following set J of h and psi. J of h and psi is the linear envelope of the set of operators of the form r eta psi, r zeta psi star, when eta and zeta belongs to dh psi, and these operators are of course operators on h, so they are part of B of h, because you have r eta going from hash psi to h, and the adjoint is going from h to h psi. So this is defined on h and has the range on h in this thing. Okay. And this is an S star dense, two-sided ideal in n prime. Okay, so why is in n prime? It's obvious from this relation here, and a relation you obtain by adjoining it. Okay. If you have positive elements in J, H, psi, they are necessarily of the form sum from finite sum from k equal to 1 to n of r eta psi, r eta psi star. So any positive element in JH psi is of this form. This you can suspect what is the proof here is a polarization relation. Okay. Let me mention one more thing, namely that there is a sequence eta k in dH psi such that the sum, but I put again S star sum from k is equal to 1 to infinity of R eta k psi R eta k psi star is equal to 1. So the finite sums here converge to the identity operator. Okay. There is just one more thing to be pointed out in this thing, namely for eta and zeta in the domain of H psi, you have R zeta psi star R eta psi, you see, is the other side, the other order, like here. You will have this thing belongs to, they are in N, but to the M of psi prime. I will say immediately what is psi prime. And psi prime of R zeta psi star R eta psi, it's equal to the scalar product eta zeta. Now, what is psi prime? Psi prime, well, let me say so. If you have a von Neumann algebra with a bicyclic vector, then this gives to you a form, a positive normal form on the algebra. But at the same time, it gives a normal positive form also on the commutant, right? So that's the form which is naturally associated to the form given by the vector on the algebra. Now, in general, if you have not a positive linear form, but you have a weight and so, you get a left Hilbert algebra. Once you get the left Hilbert algebra, you associate to it a right Hilbert algebra, right? So psi defines a left Hilbert algebra, right? The left Hilbert algebra has right Hilbert algebra associated, and this right Hilbert algebra will give rise to another form, right? So this is, in the case of a bicyclic vector, this is very simple. Omega psi 0 is 1, is this psi, and omega psi 0 prime on the commutant is the other one. So this is the meaning of psi prime in here. And that's the whole story. I prefer to have all this on the blackboard now for the next definition. And here, take it so. Okay. So now I assume that I have a von Neumann algebra M in H, in B of H. and I denote by n the commutant m prime in B of h. Okay, and we take psi and NSF weight on n, and phi just a normal semi-finite weight on m. We want to define the operator which is denoted by d phi psi. This is the goal now. And what we do the following thing. We look at the function q, which is defined on dh psi. dh psi as above for this n, which is the commutant of m. Taking an eta and going with this eta in q of eta, which is equal to phi of r eta psi times r eta psi star. And what you see in this, you see that so the domain of Q, which is dh psi, is dense in H. It's absolutely immediate to check that Q of lambda eta is equal square of the absolute value of lambda Q of eta. And Q is lower semi-continuous. And Q satisfies the parallelogram rule. Q satisfies this rule in here. So Q is a positive quadratic form, which is, because it is lower semi-continuous, it means it is closable. And by the theorem I put here, by this theorem, after that I will erase this blackboard, it follows the following thing. There is a greatest positive self-adjoint operator delta phi per psi in H, such that the domain of delta phi psi 1/2, it contains the domain of Q. I just repeat the conclusions in this theorem here. If eta belongs to dh psi, then delta phi psi 1/2 of eta, it's equal to phi of r eta psi, r eta psi star. It's just this thing. And moreover, we have the following thing. We have that the closure of delta phi per psi restricted to the domain of Q. This is equal to the whole operator delta phi psi. So now on the blackboards there is the whole information about how the operator delta phi psi, which is called the Kohn spatial derivative of phi normal semi-finite weight on M with respect to psi, which is a normal semi-finite finite weight on the commutant. So this was the construction of the operator. Now I will state the main results concerning this operator. I will state a first theorem of Kohn. The proof, well, it's in the book I indicated here. The proof is self-contained. It's indeed, it is on 3.5 pages, but it is self-contained and with all the details. And the theorem is, before that, let me give an example. The example is the following. M is B of H. So that N, which is a M prime, is just the scalars, the C times identity of H. Any normal semi-finite weight on B of H is of the form trace of A. And here you have not too many choices for a weight. It's just the identity representations. Lambda is going to lambda. I will denote it by 1. So this is for phi, this is for C. And delta, it's equal to A. It's very simple to check that with the definition I gave, but it is also relevant for what it means, this derivative. And now the theorem of Alan Kohn is the following. Notation is as above. So that means you have M in B of H, you have N, it's the commutant in B of H. You have some phi's on B of H, on M, and a fixed psi on B of H, right? Well, then...
M is for M prime or no, not opposite?
Sorry? No, it's M prime in this... well, it can be formalized also for the opposite algebra, but I work with the commutant here. So that let phi psi first both NSF. This and this are fightful. And then what you have, a first conclusion, is that the support of delta phi psi is equal to 1. That means the operator, the positive self-adjoint operator delta is non-singular. And the inverse of delta phi psi inverse, it's equal to delta psi with respect to phi. It's clear that you can do the same thing taking as the original algebra N and its commutant M. Good. A second assertion is the fact that sigma T phi, the modular automorphism group of phi of x, is delta phi psi it x delta phi psi minus it, and this happens for every x in M. So that you have a kind of a modular automorphism in a given representation of M, right? M is not in standard form where the delta phi appears or so. This is an operator on H where M acts. Okay. The third thing is the similar thing with this, namely that sigma T psi of y is equal delta phi psi minus it y delta phi psi or it for any y in N. Remember, N is M prime. And if phi1 is just normal semi-finite, immediately. Yes, Sandra.
The third equation, the left side has no phi in it.
Sorry?
In number 3,
Yeah.
the left side of the equation has no phi.
Number, do you have it here?
On the left side,
On the left side, you have no phi, of course.
or no for all.
But here you have no psi. It's the same thing. Right? Here you have no psi, here you have no phi. The delta is defined for phi and psi, and it implements the modular automorphism group of phi as well as the modular automorphism group of psi, well, with the minus t there, and that's all. Okay. And if phi is just a normal semi-finite weight on M, then what you get the following thing. The support of the operator delta phi1 psi, it's equal to the support of phi1, and delta phi1 psi to power it, it's equal to the derivative of phi1, the conderivative, the concocycle, phi1 d phi. What is phi? Phi is a fixed, was fixed at the beginning in here, but NSF. So it is this cocycle times delta phi psi to power it. And this is the main theorem concerning the spatial derivative. There is a very nice corollary which was observed by Hagerup, and maybe it will be the only proof I will give, a corollary noticed by Hagerup. It's the following thing. You have M in B of H with commutant N, it's equal M prime in B of H. And you have an SO continuous one parameter group of unitary operators. T goes in UT which is in B of H and is unitary. This is, so unitary group, say, SO continuous. One parameter, SO continuous, unitary group. And then are equivalent the following two things. First, there is a weight phi NSF on M such that sigma t phi is equal add of ut for every t in R. And the second assertion, which is equivalent to this, is that there is psi, an NSF weight on M prime, such that sigma t psi is equal add of ut star for every t in R. Having this theorem, the proof is very simple, and I will give it. Of course, it is enough to prove that I implies two I's. And then what you see, you look at this map from R, taking T into what I call W of T, which is ut star delta phi psi 0. Psi 0 is just a fixed psi 0 NSF on M prime. I'm sorry. That's okay. Psi 0 is a fixed NSF weight on M prime. Then this thing is times to power IT u t, u of t. I wrote u of t here. Belongs to M prime, which is equal to n, and it is a sigma psi 0 cocycle. Being a cocycle, it follows that there is an NSF weight psi on n such that the psi 0 t, it's equal this operator w t. And then sigma t psi of y will be equal w of t sigma t psi 0 of y w of t star. This is simply because this is a cocycle sigma t psi 0 cocycle, and this, if you do the computation, is ut star y ut, and that's the end. So that is a very simple proof, but based on a very strong theorem. Okay. Good. Let me list also some properties of this Some simple properties of this derivative are the following. If you have phi1 is less than phi2, then you have delta phi1 psi is less than delta phi2 psi. Notice that these are unbounded operators, so the inequality has the special meaning I described before in some other lecture. Then delta of phi a dot a star with respect to psi is equal to a star delta phi psi a for a in M invertible. And delta of the sum phi1 plus phi2 with respect to psi. So here you have to take care because phi1 plus phi2 is not necessarily semi-finite. So when this is a normal semi-finite weight, then what you have here, you have delta phi1 psi and delta phi2 psi, and you expect here a plus sign, but it is a plus sign with a dot which means the form sum of the unbounded operator, the positive self-adjoint operators. So that is the meaning of this notation with a dot over plus. Well, a second very important theorem of Alain Kohn is the characterization of these operators, delta phi psi. So that you have a second theorem, again by Kohn, which says the following thing. You have M in B of H. You have N, it's equal M prime in B of H. You have psi, an NSF weight on N, and A, a positive self-adjoint operator in H. Then R equivalent the following things. First, there exists psi, phi, a normal semi-finite weight on M, such that A is delta phi psi. And the second is the fact that A power it times y, it's equal sigma minus t psi of y times it. This happens for every y in N and every t. So that's a very neat characterization of what are the operators delta phi psi when psi is fixed. Well, there is a third assertion here, namely that A1/2 restricted to the domain of A1/2 intersection with dH psi, the closure of this restriction is the whole A1/2, and for every eta 1, eta n in dH psi, you should have the following fact, that the sum from k is equal to 1 up to n of A1/2 eta k square depends only on the sum from k is equal to 1 up to n, so depends only on this sum r eta k psi, r psi eta k star. Now the implications, one implies 2 and 1 implies 3, should be regarded as obvious. They are indeed obvious when you enter the problem, the situation there. So that the converses are essential here. Okay. Now I will just mention another theorem of Alan Kohn. Is a characterization of delta phi psi for phi a normal positive form. So this was a characterization in general. Psi was fixed. And there is also a characterization which is rather technical, and I will not write it in here because it has no meaning to write it. Okay. Now, as a consequence of this theorem, we have two very, very nice results, and very interesting results. Namely, you have the same situation, M in B of H. You have N is M prime in B of H. You have psi, an NSF weight on M prime, on N prime, and you have phi and phi sub k, normal semi-finite on M, normal semi-finite weights on M. Well, if phi k of x converges increasingly to phi of x for every x in M plus, then what about the modular automorphism groups of these weights, phi k and sub phi k? So that then what follows is first the thing that sigma t phi k of x converges ultra strongly star to sigma t phi of x for every x in the union of support of phi sub k, M, support of phi sub k, union of the k, and for every t in R. So that's a much expected result. Here you have a convergence of the weights, and here you have what means the convergence of the weights for the modular automorphism group. Okay, and the second result is the following. What about the conderivatives? About the conderivative is the following. D phi k with respect to another NSF weight on M, T. This converges ultra strongly star to d phi times d theta, d tau, T, where T is NSF on M. And for every T belonging to R. So, what about the modular automorphism group? What about the concocycle? And what about the spatial derivative, of course? So that the third result concerns the spatial derivatives, which says simply that delta phi k psi converges increasingly to delta phi psi. Let me recall that I gave also a precise meaning of this thing for positive self-adjoint operators, unbounded operators. So this is the first consequence, corollary 1. And here you have a corollary 2, which are in the same situation as above, but you assume that phi and phi n on M are fightful, are NSF. Okay, and psi is NSF on M, on N is equal M prime. Now, I'm sorry. Phi and phi n belong to M star plus, so they are positive forms. They are bounded weights. And then you assume if what is the natural convergence for phi and phi n is the norm convergence. Phi minus phi n in norm goes to 0, then 1, 2, 3, same as above, same as above, concerning, so this is concerning the modular automorphism group, yes, but for every x in M this time. And the third thing is that delta phi sub n with respect to psi to power it is a bounded operator, converges S star delta phi psi. Okay. So up to now we have a clear definition of what is the spatial derivative. What is the importance of the spatial derivative was the first theorem of Alencon. What is the characterization of the spatial derivative is the second theorem of Kohn with two excellent, splendid corollaries. And I will also mention one peculiar thing, namely the following. And I insist that the proofs are self-contained in the place I indicated to you. With what you know up to now, it's completely self-contained. Thank you. Bye. Okay, thank you. Now the last thing. You have Psi and NSF weight on a von Neumann algebra N in B of H. And you have T, a closed linear operator in H. And you write T is equal U, absolute value of T, the polar decomposition. Well, the operator T will called homogeneous of degree S with respect to psi, which is fixed there, if U belongs to the commutant of N and modulus of T power IT Y, it's equal to sigma ST psi of Y times absolute value of T power IT. And this happens for every Y in N and every T in R. Okay. The characterization of the operators delta, phi, psi in the theorem, the second theorem of Alain-Cohen, was the fact that these are the only positive self-adjoint operators homogeneous of degree -1. It was sigma minus T here.
And it is times T or a multiplication?
Here, it's times the absolute.
The modulus
Is S times T.
is times T.
S times T, and here is -1 times T. And in the second theorem of Alain-Cohen, the characterization of the operators delta phi psi, there exists a phi such that the operator is delta phi psi, if and only if the operator is homogeneous of degree -1. With respect, of course, with respect to psi. Okay. And for such an operator, A, which is homogeneous of degree -1, it's possible to define the integral. Integral of A d psi is by definition the sum over K of some vectors A powers 1/2 eta K. But I have to put what is eta K, and I missed this. So it's possible to define what it is, the integral. Okay. And A is called psi integrable if this integral well, let me put the definition. It's possible to define the integral as being for A homogeneous, so it is of this form, it's possible to define the integral here as phi of 1. And A is called psi integrable if phi of 1 is less than infinity. So these remarks, just remarks by Alain Cohn, led to integration theory with respect to weights. The details of his ideas here were done by Michel Hilsum. On the other hand, Hagerup found another definition of the LP spaces. He developed his theory, but this theory was much more developed and very nicely exposed by Marianne Terp. Which is a series of 4 preprints in the University of Copenhagen. These preprints appeared, I think, in 1988-89. But you can find them if you ask in the University of Copenhagen. Now, let me thank you for all your attention during these 2 weeks, and to say that this is the end of all my stories here. Thanks.